Hello everyone, this is Team 10, and for our senior design, our group has developed what we call the thermal expansion generator. Here's our information display board. We're going to dive into each piece of it in this video, explaining what our project is and how it's structured.
Fossil fuel reliance has led to serious atmospheric and geological issues. To pollute our planet less, the demand for renewable energy sources has increased. Our team aims to provide an alternative means of generating electricity from solar energy, harnessing both light and heat from the sun.
There are a few significant principles driving the design of our project. Firstly, the project namesake, thermal expansion. When the fluid within our system undergoes an increase in temperature, the fluid's volume will increase. The amount it increases depends upon beta, the coefficient of thermal expansion, a materialistic property unique to each fluid. Due to the conservation of mass, the density of the fluid decreases as the temperature increases, as the chart shows. The heating of the fluid is achieved by transferring heat energy both conductively with direct contact of metals and convectively from metal to the fluid. Finite element analysis was used to help convey thermal distribution. A user of this product is looking to generate electricity exclusively using solar energy. The design of such a product is constrained by a variety of factors related to safe operation of the system. The fluid must be maintained as a liquid to keep the cyclic nature of the project intact. The project is also very dependent upon the availability of sunlight. Additionally, selection of materials is important because we need to ensure that the metal and the fluid are compatible to avoid corrosion, and also to understand the safe range of pressure in which we can operate. Another constraint regarding the fluid is that some chemicals exhibiting a large coefficient of expansion may inhabit hazardous characteristics upon heating, so choices are limited.
The source of the heat comes from an evacuated solar heat tube, which warms up rapidly in sunlight. The evacuated tube collects heat to the aluminum nitrate material, which is then transferred by an aluminum fin to the copper heat pipe at the top. The contents inside the tube are filled with an alcohol solution which vaporizes with increased temperature. The alcohol vapor then rises to the copper bulb, where it transfers its heat from vaporization, then condenses and moves back downward. Using conductive and convective heat transfer methods, the heat energy is transferred from the copper tip to an aluminum block, in which a hole is drilled for insertion. The fluid then extracts energy as the piping passes over the block's surface, both above and below. After heating, the fluid moves into a flow-controlling bell siphon system and down over the paddles of a water wheel, which rotate gears that are connected to a generator.
For electrical generation, the self-made axial flow generator is capable of producing a testable 4.5 volts. The generator consists of 3 phases, which uses 2 coils per phase. The circuit functions using 3 full bridge rectifiers with a Zener regulator circuit to convert AC to a usable stable DC voltage.
The fluid is stored in a reservoir and then cooled down in a radiator with aluminum fins. This completes the cycle, which is regulated by a ball valve. This ensures that a temperature difference is present for the expansion to occur again.
The ball valve at the bottom of the structure is controlled by a 2-stage float switch located inside the reservoir by an STM32 microcontroller. We can communicate with the system using the UART Bluetooth module and a mobile device. Commands can be sent to check and change the status of various flags, such as forcing the valve open and closed. We can also view temperature sensor data in Celsius from 3 TMP36 temperature sensors. Using onboard timer-based interrupts, the temperature of all 3 is recorded every minute and can be requested from the mobile device. There's also a live mode in which the temperatures are reported every 5 seconds using a separate interrupt.
There are a variety of improvements that could be made on future iterations of the design. We would look to optimize the amount of solar radiation that is incident on the tube through both a tracking system and a parabolic trough. Another recommendation would be to further increase the use of sensors to track pressure, as well as to expand upon the use of existing temperature information. Quicker, stronger results could be obtained by changing the scale of the wheel and generator system. This could be done by integrating our design into existing systems. And a special thanks to Solid State Cooling Systems, Fala Technologies, and Chris Workshop for assistance with the completion of our project.